the Eternal Now and the Information-Based Universe, a research program on the block universe, quantum information, and the foundations of reality. Arşen Kaan 2025, Theoretical Physics and Cosmology Research Essay. This work presents an interdisciplinary research framework that brings together the block universe interpretation of spacetime and the hypothesis of an information-based reality. Drawing from Einstein's relativity, Wheeler's It from Bit proposal, quantum entanglement, the holographic principle, and modern developments in quantum information theory, this article explores the possibility that information may be more fundamental than spacetime itself. Rather than proposing a completed theory, the goal is to identify converging lines of research and highlight the open questions that may define the next generation of theoretical physics. Number 1. Is time really flowing? Human experience suggests that time flows. The past is gone. The present is being experienced. The future has not yet happened. This intuition is so deeply embedded in our perception that it feels almost self-evident. Yet modern physics raises a remarkable possibility. What if the flow of time is not a fundamental property of reality? Einstein's theories of special and general relativity describe time not as an independent universal clock, but as part of a unified four-dimensional structure known as spacetime. In this framework, space and time are inseparable. The consequence is profound. Many physicists and philosophers have argued that relativity naturally leads to the block universe interpretation. According to this view, past, present, and future events all exist within a four-dimensional spacetime manifold. Nothing comes into existence. Nothing passes away. Everything simply exists at different coordinates within spacetime. If this interpretation is correct, then the flow of time may not be a feature of the universe itself. Instead, it may be a feature of conscious experience. This raises one of the deepest questions in science. Is the present moment an objective property of reality, or a way consciousness processes a four-dimensional universe? Number 2. Cosmic memory. The cosmic microwave background. The oldest observable light in the universe is the cosmic microwave background, CMB. Approximately 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Photons could finally travel freely through space. Those photons still exist today. After more than 13 billion years of cosmic expansion, they now appear as microwave radiation with a temperature of approximately 2.725 Kelvin. The CMB is often described as the universe's baby picture. It contains a record of tiny density fluctuations that later evolved into galaxies, clusters, and the large-scale structure of the cosmos. From a block universe perspective, however, the CMB can be viewed differently. We are not literally looking into the past. Instead, we are observing events located at different spacetime coordinates. The distinction between past and present becomes less fundamental and more geometrical. In this view, observing the CMB is similar to examining another region of spacetime rather than accessing a vanished history. Number 3. The Planck scale, the deepest layer of reality. Modern physics is built upon two extraordinarily successful theories: general relativity, quantum mechanics. Each works remarkably well within its own domain, yet they become incompatible when applied simultaneously. The natural meeting point of these theories is known as the Planck scale. The fundamental Planck quantities are Planck length, approximately 1.616 times 10 Nsbmrsky meters; Planck time, approximately 5.39 times 10 Mendelswars seconds; Planck mass, approximately 2.176 10 mmol kilograms. At these scales, our current theories cease to provide reliable descriptions of reality. We do not know whether spacetime remains continuous. Several approaches propose different answers. Loop quantum gravity suggests spacetime may be discrete. String theory replaces particles with one-dimensional strings. Causal set theory models spacetime as a network of causal relations. Holographic approaches suggest spacetime may emerge from more fundamental informational structures. Importantly, the Planck scale does not prove that reality is made of information. Rather, it marks the frontier where current physics reaches its limits. Number 4. Wheeler's It from Bit. One of the most provocative ideas in modern physics came from John Archibald Wheeler. Wheeler proposed a simple but radical possibility. Information may be more fundamental than matter. He called this idea It from Bit. According to Wheeler, every physical object, every field, and perhaps even spacetime itself may ultimately derive from informational distinctions. In his own words, open quote, every particle, every field of force, even spacetime itself, derives its function, meaning, and existence from binary choices, from bits, close quote. This idea remains speculative. However, it has inspired multiple active research programs. Several modern developments appear surprisingly consistent with Wheeler's intuition. Black hole thermodynamics, quantum information theory, quantum computing, holography, quantum error correction, entanglement-based approaches to spacetime. Although no complete it-from-bit theory currently exists, the idea continues to influence some of the most advanced areas of theoretical physics. Number 5. The Higgs field and physical structure. In 2012, CERN confirmed the existence of the Higgs boson. This discovery completed the standard model of particle physics and provided strong evidence for the existence of the Higgs field. The Higgs field permeates all of space. Particles interacting with this field acquire mass. Its significance extends throughout modern physics. It explains the masses of W and Z bosons. It contributes to the mass hierarchy of matter. It plays a central role in electroweak symmetry breaking. Within an information-based universe framework, an intriguing question emerges. If matter and spacetime are emergent properties of a deeper informational layer, what role does the Higgs field play within that structure? At present, no answer exists, but the question remains open. Number 6. Quantum entanglement and the geometry of space. Quantum entanglement is one of the most experimentally verified and conceptually astonishing phenomena in science. Two particles can become correlated in such a way that measurements performed on one are connected to measurements performed on the other, regardless of distance. Einstein famously called this, open quote, spooky action at a distance, close quote. Bell's theorem and decades of experiments demonstrated that these correlations cannot be explained by classical local hidden variable theories. The mystery deepened further in 2013. Juan Maldacena and Leonard Susskind proposed the ER equals EPR conjecture. The idea suggests a connection between Einstein-Rosen bridges, wormholes, Einstein-Podolsky-Rosen quantum entanglement. In its strongest interpretation, entanglement and spacetime geometry may be different descriptions of the same underlying reality. If correct, spacetime itself may emerge from networks of entangled quantum states. Number 7. The holographic principle. Black holes led physicists to an extraordinary discovery. The entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This observation inspired the holographic principle. The principle suggests that all information contained within a region of space may be encoded on its boundary. In 1997, Juan Maldacena developed this idea mathematically through the AD-SCFT correspondence. This duality demonstrates an equivalence between a gravitational theory in higher dimensional spacetime, a quantum field theory living on a lower dimensional boundary. More recent research has revealed something even more surprising. The structure of spacetime geometry appears closely related to quantum error correcting codes. This suggests that spacetime may not merely contain information, it may actually be constructed from information. Number 8. The information-based universe hypothesis. Several independent research programs appear to converge toward a common theme. The block universe suggests that time may not fundamentally flow. The holographic principle suggests that spatial dimensions may emerge from deeper structures. ER equals EPR hints that geometry may emerge from entanglement. Quantum error correction suggests that spacetime behaves like an information processing system. Taken individually, none of these ideas proves that reality is fundamentally informational. Taken together, however, they suggest a remarkable possibility. Perhaps matter is not fundamental. Perhaps energy is not fundamental. Perhaps space and time themselves are not fundamental. Perhaps they are emergent manifestations of a deeper informational layer of reality. This remains a hypothesis, but it is a hypothesis increasingly difficult to ignore. Number 9. Conclusion. The next great question. Science advances not only through answers, it advances through better questions. Newton asked, what is force? Einstein asked, what is time? Today, theoretical physics may be approaching another foundational question. Is information more fundamental than spacetime itself? We do not yet know the answer. Yet many of the most productive research programs in modern physics, black hole thermodynamics, holography, quantum gravity, entanglement theory, and quantum information, appear to point toward information as a common language beneath reality. Perhaps this convergence is accidental, or perhaps it is a clue that the deepest layer of the universe is not matter, energy, space, or time, but information. And if that possibility proves correct, our understanding of reality may undergo a transformation as profound as the discoveries of Newton, Einstein, and quantum mechanics itself. Selected references: Wheeler, J.A., and Zurek, W.H., 1983. Quantum Theory and Measurement. Maldacena, J., 1997. The Large N-Limit of Superconformal Field Theories and Supergravity. Penrose, R., 2004. The Road to Reality. Suskind, L., and Maldacena, J., 2013. Cool Horizons for Entangled Black Holes. Ryu, S., and Takayanagi, T., 2006. Holographic Derivation of Entanglement Entropy from ADS-CFT. Almhiri, A., Dong, X., and Harlow, D., 2015. Bulk Locality and Quantum Error Correction in ADS-CFT. Keywords: block universe, quantum information, holographic principle, E=EPR, spacetime emergence, foundations of reality, theoretical physics, cosmology.